Do you guys remember the difference? Anyone remember the difference between the two approaches?
Bayesian based on like beliefs, like subjective frequentist was like standard formula, never outcome change, total outcome.
So yeah, so typically frequentist probabilities were thought of as runs, right? You just count up how many runs you have, and this is your probability is a notion of a frequency and a limit. Whereas in the Bayesian formulation, it was more thought of as a belief. Okay? Now, when we think about maximum likelihood estimation, okay, or even method of moments, I asked you what P is, right? What's my estimate of P? And we get, okay, well, this is my P, right? And we also had some notion of uncertainty there. Our notion of uncertainty was, should have installed the app. Okay. Every once in a while, I'm just going to move things here, so don't be too distracted. It's just so I don't have the thing go to sleep. We got a point estimate, and then what could we do with a point estimate sometimes? You guys learned about some type of interval, right? What kind of interval did you learn about? You learned about confidence intervals, right? And the idea was, well, if I do this again and again and again, right, sometimes I might get a sample, right, where my confidence interval does not fall over the true parameter, right? Like with a 95% confidence interval, 95% of the time your estimate, right, is going to fall over what? The true parameter, right? But 5% of the time it's not. Okay? So that was what we thought about, okay? The idea behind Bayesian inference is there's not necessarily a true parameter. So if I tell you about P, there may not be a true P. What I might say is that those P's come from a distribution itself. Okay? And so what I'm going to try to do is, given the observation, try to estimate that distribution of P. Okay? So what you're actually directly trying to do is manipulate the probabilities of your estimates. Okay? And so you start that. You have a probability distribution that reflects your current state of knowledge. I'll give you an example. Do I have a coin? I don't have a coin. Let's say I had a coin. Okay? Before I show you the coin, right, what is your prior probability going to be on that coin? I have a coin. What do you think my coin's going to be? You think it's going to be fair? Most likely, right? So the highest probability is probably 0.5, right? Do you think everything else is completely zero? So let's actually draw this. This is my probability P. This is how fair or unfair my coin is. Okay? What values can P take? What's the smallest value it can take? 0. What's the biggest value it can take? 1. Okay? Okay. And this is my density. This is my density on P. Okay? Alright. So let's say this is 1/2. So let's go in there. What do you think? What's the maximum value P? Do you think it's uniform? You think, I'm asking you. You can say whatever you want. What distribution do you think we should have on this coin coming in? Uniform? Okay. So one option, right? This is one. One option is the uniform. If you tell me a priori, I believe this coin is uniform, what does that mean? What does that mean? It may not be fair. I'm saying, look, I don't know anything about your coin coming in, right? I am willing to say that it is equally possible to get any value of P for this coin coming in, right? That is one notion of a prior, okay? This is called a uniform prior because it's uniform overall probability, okay? What's another way we could come in with a prior? You could center it about 1/2. How would you ration that it should really be centered around 1/2 and kind of have some standard deviation? Let's say it looks something like, I don't know, like this, right? This could be another option. How would we get this out? If someone would say, well, okay, you told me it should be centered
look like this. Why? You suggested it. Why? We can assume most coins are fair. What we can do is we can just say, hey, look, I went to the Federal Reserve or wherever they mint coins, local coin minting place, and I took, 1,400 coins, and I flipped them all, right? A bunch of times, and I got their fees, and I plotted it, and it looks like this, right? So we could use past examples or similar data to also come up like that, okay? These are the two most common ways of getting at what a notion of a prior would be. We either try to find something which is uniform or as uninformative as possible, or we try to find something that we already think is pretty true. Okay? This is saying, I don't know anything, right? This is saying, hey, I actually do know something because I know something about coins. Okay?
And that could actually happen, right? Because of the central limit theorem?
That could actually happen because of the central limit theorem, for example, yeah.
So the idea is you start with some distribution, right? Then you get data. Given the data, you update your probability, okay? So, there are many, many examples of that, and I'll go into that in a second. And you can do this basically using Bayes' theorem. And again, the key idea here is that you're holding on to a distribution. I currently have a distribution of what I think P is, right? I see a new coin, and then I update what's going on. So let's give an example. Let's say that there are two possible. Let's say you're watching a basketball game, and there are one of two people that could come up and be shooting a free throw. Okay? And a priori you don't know who it is, right? But you have kind of average free throw probabilities of an average player. Okay? Now, if it's a person who's really good at free throws, right, they come up and they make two in a row, you'd probably update your probability towards this being the person who's better, right, next time they come up. If it were someone, this will date me, but like Shaquille O'Neal, who would miss a lot of free throws, then you'd probably weight it down. So the next time this person comes up, you'd weight P down, right? So there's actually ways of doing this, and that's what we're going to talk about. Okay. So we're going to use Bayes' theorem to do this. So D is an event. It's something that happens or it doesn't. Okay? Guys, remember these mutually exclusive events? Okay? So you can think of these as competing hypotheses. So one way of thinking about Bayes' rule is think of D as data. I observe D, right? And given D, I want to say which one of these mutually competing hypotheses are true, right? So in this case, given D, was this person a good free throw shooter or a bad free throw shooter, for example, right? Did this person have a higher probability of getting P or lower P, okay? And this is just Bayes' rule, okay? And there are two ways of thinking about it. One way is with the normalizing constant, and the other way is without. So this is just proportional to. Okay? Why sometimes may you not care about the normalizing constant? Let me rewrite this in a certain way. This was written as probability of AJ given D, right? We could also think about this sometimes as a probability of theta given data. If AJ, so this is my parameter, and this is my data. Okay? So we can ask about the probability of the parameter given your observation. Okay, that's another way we could have thought about it. And the reason why sometimes we're happy enough just to get something proportional is what? Let's say I'm comparing three different thetas. let's say I'm comparing, let's say I want to compare theta 1, comma, theta 2, comma, theta 3. Okay? I want to know which has a higher probability, right? Or I'm comparing 3 partitions. I'm asking you which has a higher probability. Okay? To compare them, do I need the denominator?
No.
Is the denominator different for all of those? It's the same denominator, right? So one of the reasons why a lot of times we don't need this denominator is if we're just asking for which one is the biggest, right? Well, just compare them, just take the biggest one. Because you're dividing by the same denominator for all of them. Okay? So if you actually don't exactly care what this number is, right? But you care where it's the largest, or you care about the distribution, what it looks like, then you don't need the denominator. And that'll be relevant soon. Okay. So I think I said this. A1 through AJ are the possible states of nature. You can also think of those as your parameters. Those are the different parameters that could have given rise to the data. Okay? Okay, so let's go through some terminology. So wherever you see AJ there, I might just write down theta. Okay, so just think of AJ and theta as really equivalent, okay? So we have something which is called a likelihood, which is actually the same likelihood as I just talked about. And here we're going to think of that as a probability of your data given a parameter. So theta is your parameter or the state of nature, right? So this is saying that, hey, if state of nature were this theta or this AJ, right? This would be the probability of observing this data. So this is your likelihood, okay? Data given theta. Then we have a prior. This is my prior probability of the states of nature, or my parameters, right? In the case of coin flip, it would be something between 0 and 1, so on and so forth, okay? Then there's a probability of data, okay? Which is the marginal probability. Why is this a marginal probability? You guys remember what we did with marginal probabilities? If I have a probability of x comma y, right? I could give you a marginal probability of x or a marginal probability of y, right? So this is a marginal probability of, I have 2 variables here, right? What are my variables? A and D, right? Or theta and D, however you want to think about it. And what we're saying is that this is a marginal probability of the data. And then we have something that's called a posterior probability. And anyone want to take a guess what the posterior probability is? It's going to be the probability of theta given D. So before I saw any data, right, this is my state of the world, right? This is the states of the parameters. This is the distribution I put on the parameters, okay? After I see data, I can update it and get this. Okay, what's the formula to update it? Anyone want to take a guess? How I go from the prior to the posterior? You're going to use Bayes' rule. Yeah, exactly. And I think we do that on the next slide. We actually don't do that on the next slide. So let's do that on the board, and then we'll go to the next slide. Okay, so you guys are okay with this, me writing down Bayes' rule this way? Okay, so let's go through the terms in here, okay? What's the probability of d given theta? What is this called? This had a name, right? What is this called? It's called the likelihood. Okay? What's the probability of theta? This also had a name. It was called the prior. Okay, what's the probability of d? This had a name too. What's probability of d? The marginal. Should we write down? Do you guys remember how to write down the probability of d? What's this equal to? This is going to be an integral of what?
Over theta.
Integral over theta of what? Of the joint, right? Of probability of theta comma d. Right? And then what am I going to have here? D theta, right? Okay? Okay. And this was called the, this is called my posterior probability. Okay? Okay. So you start with some distribution over your states, over your parameters. Then when you get data, you update with it. You update it with the likelihood. Okay? What's the alternative form that we saw? That was one way we wrote it. What was the other way we wrote down? Probability? In the posterior, I could write down probability of theta given d is proportional to, remember I said sometimes we'll just use a proportional to? And then what did we not include when we included the proportional to? We forgot about the marginal, right? The P of D. We just said this is proportional to the probability of D given theta, probability of theta. Okay? So we didn't include that normalization. Okay. Now we need to talk about a few things that are relevant for your, what is that thing called tomorrow? Your lab tomorrow, okay? That also have to do with Bayesian. Okay, you guys know what odds and log odds are? No, okay. So this actually came up in horse betting. This is, I think, where they, in gambling and horse betting is when they first came up with odds and log odds. But let's say my event A is heads or tails. Okay? So it either it happens with probability P. Okay. So the odds of getting a heads is equal to the probability of getting heads divided by 1 minus the probability of getting heads. Okay? So what is odds doing? One way of thinking about probability of getting heads is a number between 0 and 1, right? You guys are all okay with this? Okay. What is this number? What number are the odds between? What's the largest the odds can be? Anyone?
Infinity.
It could be infinity, right? When would it be infinity? If the probability of A is equal to?
1.
1. Okay, good. So the odds go between infinity and what? What's the smallest the odds can be? 0. Okay? So it maps something that went between 0 and 1 to something that's not between 0 and infinity. Okay, so that's what the odds ratios are. Okay? And so you have that, okay? So here's an example. The probability that a horse wins a race is 0.05. Then the odds of that horse winning the race are or 1 in 19, right? So if you actually read like if you read newspapers and read any lines on sports events, they often write it in odds. They don't write it as the probability of winning is 0.05. They actually say that, the chance of this team is 1 in 19, 1 in 7, 1 in 5. Sometimes you see 2 in 7, things like that, right? And that's what is meant by the odds ratio. Okay, now, often a pretty relevant number is the log 10 of the odds, which is called the log odds, okay? What values does a log odds take? What's the largest the log odds can be? Log of infinity is infinity. Log of 0 is? Log of 0 is not 1. Log of 0 is negative infinity. Right? So log odds take what values? They take the values from infinity to negative infinity. Okay? So the reason why log odds are useful is they took this p, right, which used to be between 0 and 1, and now maps it to real lines, right? And things that are really, really big, if the log odds are huge, what does that mean about event A? It's probably going to happen, right? If the log odds are really, 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 really small, like negative 9,522, then what's true about event A? It's probably not going to happen, okay? And if I have a log odds of 0, right? What odds does that correspond to? Log odds 0 correspond to odds of, the log of 1 is equal to 0, right? So if you have a coin that's absolutely fair, if I have a coin that's 0.5 probability, okay? What's its odds ratio? It's going to be 0.5 over 0.5, which is 1, and the log of that is 0, right? So something that we really are absolutely completely uncertain about, whether it's going to be heads or tails, it's going to fall right in the middle, and it's going to have log odds of 0, okay? Often we think about log odds as evidence, okay? And so these are objects that we update. And you'll actually be doing this in your lab tomorrow, okay? You'll be updating these log odds, okay? There's another reason why you might want to update the log odds. Summing up log odds is equivalent to doing what to odds? Multiplying them, right? If I sum the log of something, that's equivalent to multiplying those things together, okay? So, one of the important, an important point is whenever you multiply anything, right? What happens if you multiply anything by something really near 0? What can happen? Anyone? I have 10 numbers, right? If I multiply 10 numbers together, one of those numbers were near 0. What's going to happen to this product? It could be 0, right, just by rounding error. Okay? What happens if I took the log of them, added them, right, and then exponentiated them? The chances of that rounding error go way down. Okay? So back in the day, when people try to do multiplication using log tables, right, that's actually one of the reasons why. You got a lot better precision. Okay? But anyways, that's an aside. Okay, so here's an example. I have 2 urns. You guys all know what an urn is, right? We went over what an urn is. So I have 2 urns. A1 has 70% dark items and 30% white items. A2 is 50-50. Okay? I'm going to give you one of these 2 urns. Okay? before I show you, before I give you an earn, I ask you, what is your prior probability, right, on the log odds? What are your prior odds? Right? So if it really were a 1, what would your prior odds be? It would be that what? It would just be this, right? If you, okay. You think it's coming from A1, right? What do we know about A1? Okay, sorry. I wrote this wrong. Oh wait, no, I didn't write it wrong. Okay. Let me restate this, okay? Let me speak clearly. There are two earns, right? What are our two earns? A1 and A2, right? What I'm asking you is, a priori, what's a reasonable a priori model to have of whether I'm giving you A1 or A2? Uniform, right? With equal probability I give you A1, equal probability I give you A2, right? Is that okay with people? Okay. So if that's the case, then what are the odds of getting A1? Right? The odds of getting A1 are equal to 0, right?
1.
I'm sorry, it was equal to 1, yeah. Because it's 0.5 over 0.5, right? And so the evidence or the log odds is 0. Okay? Now what we do is we have an item, we draw it from the urn, and it's found to be dark. So we're going to ask, what's the probability, the odds, and the evidence that the urn is A1? Okay? So should we try to go through that? Let's see. You guys have a quiz. We'll go through part of it, then I'll give you the quiz, okay? We'll at least start.
You could just skip the whole thing and skip the quiz.
Huh?
You could just skip the quiz and go through the whole thing.
I could just skip the quiz and go through the whole thing.
Sake of the babies.
Alright, so yeah. I don't know what to say to that. Okay, so let's write down the things we want to know, okay? So you want the probability, the odds, and the evidence that the urn is A1, right? So the first statement is we want to know the probability of what? A1 given what? Given
D1.
D equals what is it? It's dark? D1, okay, given D1. Right? So that's a probability. Okay? What's the odds gonna be? What's gonna be the odds? The odd of A1 is gonna be equal to what? Probability of A1 given D divided by what? 1 minus
the probability of
A1 given D, okay? And then the log odds is just the log of the stuff. Alright? So what do we need to do first, you think? Compute this, right? How would you compute probability of A1 given D? Okay? Probability of A1 given D, what's this equal to?
Probability.
It's equal to the probability of what? D, I'm sorry, just D1. D1 given A1, right? Times what? Probability of A1 divided by the sum over what? It's going to be the probability of D1 given A1 times the probability of A1, right? Plus the probability of D1 given A2, probability of A2, right? Okay, so let's start writing things down. Do you guys know what the probability of A1 is? What's the probability of A1?
0.5.
0.5, okay, good, we know that one. What's the probability of D1 given A1? 0.7, right? Because the probability for that one was 0.7, okay? So what else do I need now? I have D1 given A1, I have A1, okay? Do I need the probability of A2?
Yes.
I do because of the denominator, right? What's the probability of A2?
0.5.
Of A2 equals 0.5. Okay, what's the probability of D1 given A2? What's that equal to?
0.5.
0.5, right? So let's see if this was,
What is
we actually
D1?
have this worked through.
We're currently solving.
And there you go. So the probability of A1 given D1 is the following. I think this is what we wrote down, right?
Yeah.
So what's the odds? It's 1.4. And this is the log odds. Right? So we knew that there are more dark urns in urn 1, right? And so this increases our belief that it's coming from the urn with more dark ones. Okay? We'll do this next time. Okay? This is when we just observe one thing. Now what we're going to do is do it again, right? Observe another thing and update our probability. But we'll do that next time. So this time, I'll pass out some quizzes.
Wish me luck.